The typical optocoupler is usually a 6-pin device that has generally an LED infrared emitter and some type of light sensor. If we turn on the LED, it turns on the light sensor. The light sensor can be a transistor or it can be any number of things. The big advantage of optocouplers is electrical and noise isolation. The isolation potential can go up into thousands of volts. Some of them are rated at 7 or 10,000 volts electrical isolation. As shown here, it can be a number of detectors. It could be a light-activated SCR, could be a digital output, could be a Darlington transistor. There's all kinds of detectors, but they all have the basic same purpose: voltage isolation between input and output. For example, this part number H11AA1 has dual back-to-back infrared emitters. Quite handy for making things such as a zero crossing detector. Sometimes we will use optocouplers in conjunction with secondary components to make solid-state relays. What you're seeing pictured here is an input protection circuit. It can work with any of these optocouplers. They can have a range from 3 to 30 volts. Either though the LED itself has a rating of probably 1.2 to 1.8 volts, the addition of this 2-watt resistor and Q1, which is an NPN transistor like a 2N2222, as the voltage increases, the current flow will increase through the LED. And of course, it creates a larger voltage drop across this 47 ohm resistor, cutting this transistor Q1 on and shunting the current through Q1 instead of the LED. That's how your protection circuit works. This is your very most basic optocoupler circuit. Generally, we tie the LED through a resistor to ground and connect it to generally an I/O pin of an Arduino, PIC, or whatever. A high, of course, 5 volts or 3 or whatever you're using, turns the LED on. The LED light onto the base of an internal phototransistor cuts on the phototransistor and completing a path to ground. This circuit is fine, except it suffers from low power handling capabilities. Optocouplers are generally low power devices. So we have to look into using optocouplers to control more powerful devices to really handle heavy jobs. This particular one, the 4N25, is rated at 30 volts. I'm referring to the detector transistor at 150 milliamps. Not a lot of power. Alright, what we have done here is our 4N25 optocoupler. We have connected it off to 24 volts VCC, and through the collector and through the emitter we've connected a 1K resistor to the base of a TIP120. This is a power Darlington transistor rated, I think, at 5 amps. When I have a high on the LED, it switches on. It switches on the detector transistor, creates a base emitter current flow through the transistor, and switches on the lamp, in this case a light bulb. Here is another variation of the same circuit, except this time we are using a Pnp Darlington transistor, such as a TIP125. Notice something different about this circuit as opposed to the previous circuit. This circuit had the same electrical ground on the microcontroller and the secondary output at the 24 volts. Here we have completely severed the secondary power supply totally from the microprocessor. There is no electrical connection. There is only a light connection. Again, I could have done this very same thing with the Pnp Darlington that we saw earlier. A variation of this is called a solid-state relay and can use a plain old Pnp transistor if you want to. Here is another variation using this time an N-channel MOSFET. What am I doing here? I'm using the 4N25 when I switch it on to apply a voltage to the gate of Q1, the MOSFET. If it will immediately turn it on, it will create a current path and light up the light bulb. It's that simple. Be careful though. You need to read the VGS rating, that's voltage gain source, in the MOSFET spec sheet. Do not exceed it. Most of the ones I use in my videos is rated for right at 24 volts. Don't run them at 24 volts if you're using those particular ones. Here again is we're using a P-channel power MOSFET as opposed to an N-channel. It's wired differently, of course. What I have to do is I'm using the detector in the MOSFET and the optocoupler to drop the gate voltage to about a half a volt when it switches on. And this will create a difference of around 10, 11 volts between gate and source. It will switch on the transistor and the light bulb will light up. This goes right back to your basic transistor theory. Here is another variation of using an optocoupler. This time we're going to use it, connect the collector of the optocoupler detector right to the collector of the transistor. And of course the emitter through a 1K resistor is going to switch on Q1. This is really a solid-state relay. I use this in several of my other projects and videos. Note something with all of these circuits that I've just went through. Unless you've put capacitors or something in them, you can pulse width modulate them. So I can use this as a switch in either the high side or low side of a load, and I can pulse width modulate it if I want to. And this shows you the current flow here. This switches on. Get the base current here, switches on. I get the collector current. Actually, it's IE, not IC, but they're pretty much the same thing. This gives you an illustration of how it works in loads. Okay, this could easily have been a push button switch that you see here. Here is our motor. Here is our common for the power supply. You notice that I can place the transistor collector emitter from the previous circuit here. I can place it on the ground side. I can place it on the high or VCC side as long as I observe polarity. And it works just like a push button switch. And all of this is isolated from your microcontroller. Boy, that makes things a lot easier. Here is a, I guess you could say it's a fairly well complete solid state DC relay. Here is the protection circuit we talked about earlier. Here is our optocoupler, and here is our transistor switch. These I have built this. It works just fine. Alright, here's another variation of an optocoupler, but I won't go much into these. They use phototriacs or photodiacs, and they are used with triacs and or SCRs to create solid-state AC relays. That's going to be a different video, but it's pretty much the same circuit on the left side, and we will go over how triacs and SCRs work in separate videos. And that's this brief introduction to optocouplers. My website has a whole page of circuit examples and what we just went over. And now let's watch a couple of short video clips that I added onto this using optocouplers to control light and motors and various other devices.
Anyway, let's give this a little test run just to let you see what it can do. Power is on. You notice I got a little sort of alt UV LED down there. Hey, they're useful for something. This is designed to be later on to operate an H-bridge. But what I want to do is just, if you look out here, you'll see an LED come on. And you'll notice this lights up. This is just an LED across. What I'm doing is reading one of the analog input channel. I'm reading the value on this pot to control the pulse width modulation out. I can control it on and off. Now the trick is, when I program this particular PIC chip, that if I have to have both either one or the other outputs on. You'll see it over there is the green one. I got to have one or the other on. It's programmed to kill the pulse width modulation out if none of the other two outputs are working. Those will later go on to an H-bridge that I will demonstrate. Nothing much here. It works, it seems, quite well. If you look further up, it has a 12-volt power supply. The important part to note in this circuit is the opto-isolator here. Everything on that side of the opto-isolator is 5 volts. Everything on this side, here, back through there, is 12 volts. So I can have really nice control of higher voltage circuits by using an optocoupler. Again, here is an overall picture of it once again. And you can see the light bars go on and off depending on polarity. The important part about this is all this 12 volt circuitry over here. The motor, the H-bridge is only a section of this board, by the way. The power control circuit, the H-bridge, the motor, all of this stuff is completely isolated from all the 5 volt circuitry on the PIC or Arduino or whatever you're using.